All right, do I just go? Okay. All right. Hey, folks. So welcome to applying machine learning to IoT using use cases with Eclipse Deeplearning4j. So I'm a little outside the IoT space. So I'm not like hardcore on the industrial IoT side on the last presentation here. So I'm definitely more of an outsider. So I'm definitely more on kind of what I'll call the server side, bits of embedded. That being said, I am the original creator of DL4j. So if you have any questions about the internals or anything, let me know. Also, I'm one of the machine learning space's skeptics. So I hate a lot of the hype that's out there today, like, oh, cognizant AI and all that other stuff. So I'm fairly down to earth, fairly pragmatic about kind of the use cases, what's out there today. I will be putting some diagrams out there to illustrate some stuff, but it's not really to try to draw on the hype, but just more of an illustrative example of what do we do in these systems. So today's talk is going to more cover, it's going to assume you don't know machine learning, you don't know anything about the space, you don't even know like what's a model, what do I do with it, et cetera. So hopefully this will be a good illustrative example of just kind of, if you haven't seen machine learning before, what do you do with it? So as far as I know, we're the first machine learning framework at the Eclipse Foundation. So bit of an interesting story with Eclipse. I met Mike actually in 2017, and he kind of convinced me to come over. So, because I actually like their friendliness with the Java community. We're actually very close more with the Java community than we are mainstream Python machine learning and all that you hear about with today. So getting into it. So I want to start with the context. So ML software, right? So what do you got out there? So you got the kind of the machine learning and deep learning frameworks. What are these things? So machine learning, deep learning frameworks, generally very math-oriented, heavily linear algebra based, usually not very friendly to beginners. But maybe if you're on Kaggle, maybe you learn a little bit about, maybe you learn a thing or two about data analysis. Maybe you learn a thing or two about how do I set up like a machine learning pipeline. Like how do I do something as basic as detecting whether a customer is going to leave my service or not? How do I solve a simple problem, right? So you can do all that all the way to generating deepfakes with the latest TensorFlow repository. So you can either kind of participate in the hype and all the art and all the other fun stuff you see in the news, or you can do what most people do. Most people aren't actually deploying even deep learning. I can tell you that for a fact. 99% of the model is actually doing linear regression in Excel. So if you want to get into machine learning, use Excel first. If you can code, then go a step further and get into scikit-learn. But whatever you do, actually don't do deep learning. Don't use my framework. I'm not the first thing you should be using. Deep learning can be applicable to specific problems. Where 99.9% of the time when you hear about deep learning, chances are it's on vision. And it also might be on speech. It is applicable to a lot of problems, including time series forecasting of problems of different kinds that I'll get into in a little later. But in general, it shouldn't be the first technique you use. Yes, it is widely applicable. And I built the framework kind of to fulfill kind of an interesting case where I had already been doing machine learning for years. So I wanted to move away from that towards more production systems. So ironically, I had actually been doing all my machine learning in Java. And so there was, at the time, there was Python and Lua. This is 2013, and I decided to build the thing for Java. And we're the #1 framework on the Java virtual machine today. Used everything from Spark to JVM-based microservices, and even Raspberry Pis, which I'll show later as well. So beyond that, you have a little bit on the model development workflow. So what do all these buzzwords mean up here? So model development. Model development is, okay, this is 99% of the thing you hear about. I built a model that did X. You never hear about how you deploy it. So the previous talk covered a lot about kind of messy systems. That's more on the side of things that I'll be covering as well. So I'm not here to teach you how to build a model. This is a concept. And if you want, there's plenty of tutorials and other things I can recommend online for getting started. And I can help you tell the difference between this will help you build real problem or real systems. This will not. This is toy. This is real, right? So starting with feature extraction. Expanding on that a bit. This is where you spend 80% of your time actually. You're not 80% of the time when you're doing machine learning, you're not doing machine learning. Actually, what you're doing is you're dealing with messy data. Because if you have tons of data coming from different sensor networks, chances are for your specific use case, there's a particular pattern you're trying to find. Ultimately, just remember, machine learning is just dumb number crunching. That's literally all it is. It's dumb number crunching plus some statistics. That's literally what you're doing. The goal in machine learning is generally to find a signal. It's not Skynet. It's just to it's solving yes or no. It's like, this is yes or no, or I'm trying to forecast something. That's what it is. 99% of the time, that is what it is. You're trying to find a target pattern. So it could be detecting, it could be dynamically detecting faulty equipment on your IoT network. It could be using input from cameras to figure out is there an intruder or not, or are there crows messing with my machines using simple object recognition, right? And if you build something, chances are you're just building it to detect a crow. That's it. Machine learning is dumb. Computers are dumb. They are not cognizant. They are dumb. Machine learning is very dumb and very brittle. You need to always improve. You need to always be improving your models, et cetera. That's why there's a whole workflow built around this. Next, you're importing your model. So that's another thing you may do. Another thing people don't tell you in the space is when you're doing deep learning, people don't build their models from scratch. They download something from the internet. Usually there's a pre-trained model. 99% of the time, that's computer vision. Chances are it's a CNN architecture. When people say, I built a CNN, actually 99% of the time, they didn't build it from scratch. They downloaded it from the internet and followed a paper. That's what everybody does, right? So what you might do is you might import your baseline, and then all you might do is just, if you're building like a new object recognizer, chances are you're not starting from scratch. Instead, you're just improving an existing one. So you're doing something called transfer learning. Then you'll train a model. Again, whenever you hear about, it takes days to train on a GPU or whatever else, or sometimes you'll hear, it takes seconds, right? Most people don't take days to run on GPUs. Most problems aren't actually that hard. People don't have hard problems, at least the ones they want to solve. They pretend they do to write a blog post. I'll just tell you, the overwhelming majority of people out there on the internet just want to solve a yes or no problem, detect a crow and things like that. But you know what? That's still obscenely hard because it still requires understanding a lot of the math and everything else. That's why they download a pre-trained model and adapt it and follow a tutorial, right? But then people don't know how to customize it. And there's a lot of other problems that you run into when you're training models. So that's a whole black box discipline I can tell you about anytime you want. I just want you to know that most problems aren't hard, but even solving hard problems is hard. Or even solving basic problems is hard. Because you got like tune your model, like hyperparameter optimization. You hear about the AutoML stuff. AutoML doesn't actually work yet. It's getting there. But always have a human supervising it. AutoML doesn't work either. It'll work for basic problems, but it's a tool, right? So most of the time, most of the people are still kind of hand-tuning their models yet. But when you get into production, so what are you doing? So what are the mathematicians who build these models and write the blog posts not thinking about? Deploying the model, that's the easy part, right? Well, in reality, data changes over time. So you may have domain shift. Domain shift could be a sensor breaking. A sensor breaking could be new data. What do you do with it? How do you make models actually robust? Well, you need to retrain the model and update it. All of a sudden, you need to start treating a model like an asset. Well, then, what do I do with that? Well, you need to start thinking about how do I update it? How often? What happens if an update fails? What happens if the update has bad data, right? There's a lot of there's a lot of variance that you need to really think about even when you're deploying to production. So that's why you monitor model performance, right? You model accuracy over time because you know what? Especially in IoT, stuff changes. Model versioning, this is why you version models. Versioning is just where, okay, you know, I deployed I deployed version 2, but version 2 is not as accurate, so I need to roll back to version 1. Treat it kind of like, you know, standard software engineering practices. Version your code, version your models. You know, a lot of standard software engineering intuitions apply here. And finally, job scheduling. So what is this for? Job scheduling is, you know, I have a large SQL query I need to run over a, you know, huge amount of data from, you know, maybe sitting on an OSI soft cluster or whatever. A lot of the other vendors that were mentioned before. You run a batch job and you calculate, you know, this pattern for the last 5 days. Maybe that takes an hour to run. That's a batch job, right? Another one could be training. So I have a ton of data. You know, maybe I just have like a terabyte of data or a petabyte or what have you. I mean, it really depends on the scale. Again, most people don't have petabyte scale problems. You know, they want to run a job at a desired time offline. Anything could be a job, so to speak. But those things all require infrastructure. They require an IT department. They require data privacy, perhaps. You know, because actually, you know, one of the things I run into pretty often is when we're going to deploy or even just going to work with machine learning in general, the bottleneck might actually just be the corporation's bureaucracy. I can't get the data because it takes 3 months. That may be my bottleneck. It may not be even the software, right? Like, so a lot of boring things will actually slow down even doing a machine learning project. So it's just something to think about as there's a lot more to this, right? But this is kind of the overall just ML software in general. So here's that workflow a little more crystallized. So sequentially from left to right, it's kind of what I described. You know, you have your prototyping. So what they don't tell you is this is one team, this is another. So like I said, 99% of the people read the blog post. It's by the people over here writing a bunch of math, right? These are the people doing data analysis. These are not software engineers. They think they are. A lot of the times they think they are. A lot of times, you know, what I'll tell you about data science, chances are those people just came from MATLAB. If you picture them, every time you talk to a data scientist and they're building the models, picture them 90% of the time as a MATLAB programmer. That is a very good picture of the level of software engineering it takes. And honestly, you know what? It doesn't take that much to reason about building models, actually. Like, because the libraries have made it very easy, right? That's the point. It's good that these people are doing this now, right? Like, so it's you know, we in a way, we do kind of laugh. But in general, just remember, they more know the math than they know the software engineering. These people can be taught. They are smart, but they come from a different domain. They mainly know math. You know what? But that should be their job, right? Over here, you know, then we have software engineers. We have the IT. We have the scaling and all that other fun stuff. The cloud, the on-premise deployments, the whatever, right? But you know, the key to success is actually these people working together. You know, so one area where they overlap actually is in, I noticed that for some reason the data is, like I said, like I mentioned domain drift earlier. You know, so how do I get some slightly sophisticated infrastructure in production to do retraining and adjustment and things like that, right? So just think about that So just to give you an idea, I built DL4j to fulfill this whole workflow. So we have a component for pretty much all this, from the prototyping all the way up to you know, retraining and production and all that other fun stuff. So where does this workflow meet IoT? Well, data ingest and prep. So we're not going to fully prepare the data at the edge, but for example, if we can avoid sending bad data to remote systems, maybe through MQTT, for example, if we can avoid sending bad data by aggregating it or things like that, or maybe making sure the data is not redundant, noisy, that's good, right? Because you know, ultimately, machine learning is where it is bad is when you have messy data coming in, because that means that some software engineer on the other side managing the servers is going to have to clean everything up, right? Like so, some sort of ingest is generally what we're thinking about. Like if you want to think about MQTT and where it kind of meets like the previous thing, you know, that would be kind of obtain and accumulate data, right? Yeah. So yeah, I'm kind of hand waving that part, right? But I will tell you, I will say that is hard, right? And it's going to be relative to your organization and your problem, right? Like so, again, what I'm trying to do is I'm assuming no one here knows machine learning, and I just want to give you what does it look like. That's purely it. If you have some specific questions, I've done everything from deploy large retail and search systems, all the way to doing a lot of embedded stuff. I also do everything from write GPU C code to writing distributed Spark code. So Deal4j has everything up and down the stack, everything from low embedded all the way up to thousands of nodes. I've seen everything. So if you have a particular question, I'll answer it. But for the most part, like I said, the intention of this presentation is meant to be very high level. So beyond that, again, streaming platforms with some machine learning. So one thing I liked about the last talk was kind of making fun of it's like here's all these architecture diagrams and all that other fun stuff. I think every streaming platform has an MQTT adapter. But the vendor implementing that has no clue what it's actually going to take to be like, okay, we do MQTT just like everybody else. Now what do we do? How do we set up a sample use case? So I will say that is true. Actually, the software vendors, including me, have no clue what's going on over there. We can connect to it. To us, it's just a protocol. Like once you're speaking TCP, you're in MySpace now. So I can do that, right? That's my main thing I do. But I'll say in general, where we do kind of overlap is okay. Once we're allowed to somehow get data from the magical edge, then we can start doing some cool stuff. Then we can start doing pattern recognition in semi-real time, right? Like so, when I say semi-real time, I mean realistic for the actual customer's use case. So we're not doing everything in nanoseconds, right? No one needs that. You need it you might need it within a minute, whatever. You set the time though. You set the aggregation window, whatever. So you define real time as it is for your scenario though, right? There's a lot of things just to think about, like subtleties, especially with like retraining and things like that. It's not efficient to send one thing at a time. You're going to usually want to send batches. And actually, one interesting thing about that is when you efficiently send batches, there's actually both software engineering constraints, like over the network and things like that, as well as mathematical constraints. So, for example, when I actually do want to call retraining, is my batch balanced? So if I'm doing a 3-class machine learning problem, do I have a representative sample of my data to do retraining at all? So don't just retrain on whatever you're given. Validate it, set it up, aggregate it, right? So the basic batch machine learning principles still apply. So if you guys are somewhat familiar with it, in machine learning we have this idea of a train, test, and validation set, right? Like so, and those sets better be balanced. Otherwise, when you have an unbalanced machine learning problem, it either overfits or it ends up, or somehow the model ends up basically it's not accurate anymore, right? So imagine if you train a person detector and only feed it women, only feed it people of particular races, right? That's an unbalanced model, right? You want a balanced data set. So make it a representative sample. So representative sample in statistics is just a small number of examples that approximate the broader population, right? Like so whenever you get a batch in, don't just ingest everything once and just, okay, train, go, go, go. Update the model as much as possible. Don't do that. Instead, focus on applying first principles. Just because you can do it doesn't mean you should. Sometimes you may not even want to do this. Again, it really depends on your scenario. So here's the architectures we're gonna make fun of now. So again, the goal is just to, so I'm gonna hand wave this whole concept of devices and gateways, right? So the idea is to show where does machine learning and all that other fun stuff fit in. So to me, think of this as the data loading part. So we have, so Kapua is one of the Kapua's out there is like, that's one of the IoT things, Cupid. So to us, it's all brokers and message queues, basically, right? The only thing I care about is, where's my stream of data, right? Like, so that's all going to happen from, the thing where we kind of sit in the middle is, we can connect to this, we can connect to whatever message broker you got, right? And then train on, and then consume from that, right? So generally what you do in machine learning is you basically, like, you may set up like Spark streaming or something like that. This is what a data engineer does. Like, they get the model from the data scientist. They somehow they set up a workflow that productionizes it. They connect it to something like Spark. So you may have a broker that connects to something like Spark, and then Spark is what runs some computation to like aggregate the data or what have you, feeds it into a machine learning workflow, and that's generally Kafka plus Spark streaming. That's like the off-the-shelf basic thing that you're typically going to do in a given day. Another thing you may do is you may aggregate the data in Elastic to say, like, is it accurate? Is it, it's really going to depend on your use case. And then generally when you're storing things, you're generally putting things in just like an S3 bucket, HDFS. Really depends again on your use case. But again, think of this as very simple. We have industrial IoT. We have generally something like MQTT. We have brokers that may or may not speak MQTT. Eventually, you connect to something that actually does the data loading, and then that feeds the models, and then generally you consume the output via some dashboard. So what is on that dashboard? So again, that's generally latency. So you might have network statistics, and you might have other things. If you're sophisticated, you might have other things like model accuracy and things like that over time. So what could this be used for? Monitoring a factory. So if or for example, is one of my belts overheating, right? Like, so all you would really do is you'd train a basic model that just looks for spikes in temperature, right? Like, so rather than something a little more sophisticated than just say moving averages, right? Like, so you do you might get a little more sophisticated and say you start doing traffic flow optimization. So I'll actually show that later. So if I want to optimize for the amount, if I'm doing smart cities, and I want to look at the number, if I want to minimize the amount of traffic, like people waiting at traffic lights, how do I do that? There's a mix of cameras and sensors that may need to go into that. Again, security. So if you're doing networked cameras, should this person be in the factory or not? Should this person be on the floor? Maybe face recognition. This obviously gets a little scary when you look a little further out, so I won't say much, but you can see where this could go. From there, detecting electricity theft, these are all things we've done, right? Like, so another thing we've done is for one of the providers of power in China, we actually helped them detect thieves on the power grid, right? Like, so we actually looked at data from houses, and we actually detected, oh, there's a thief. There's someone actually stealing power. And so we did that. So when you start, all of a sudden you start getting, you can start to see kind of some of the use cases out there, right? Like, so it's a mix of, it's basically though, it boils down to what's going on my network. Whether my IoT network is a set of power plants, houses, buildings, or even agriculture. Right, like, so are my tractors breaking down? If you're doing drones, you're doing your flyover and you're looking for unhealthy crops, right? That's essentially an object recognition problem, sick or no, right? Like, so there's a lot of, again, you'll notice the way I'm framing these things is like electricity theft, yes or no. Networked cameras, it's going to depend on the use case, but again, it's generally some sort of a recognition or a yes or no problem. Right? Like, these are not Skynet. Right? Again, these are yes or no. You detect this very specific pattern. Here's the data. Here's the labels. Make it work. Run. That is generally machine learning. If your takeaway is anything today, that's machine learning, right? The hard part is setting all the infrastructure up, right? It's not necessarily building the model, right? What I will say is at a company level, it may just be getting a bunch of math people to work together with the IT group. That may be the hardest part about actually setting up. That's actually the hardest part about setting up machine learning at any company or even any machine learning project. Because a lot of the math people, they don't want to do the software engineering, or they're being forced to do it even though they're new to it, right? The software engineers don't really know the math, but maybe they want to learn it, right? So generally it's just, how do I speak your language? Because you may get that prototype out there, but is it robust? The guys monitoring the dashboards, like the software engineers, how do they know when it's robust? I mean, you have a lot of vendors saying, oh, we can completely get rid of the software engineer, the data scientist, and only the data scientist is needed. Oh no, don't just have the data scientist involved, especially when you get down to customer critical scenarios. Always get a software engineer involved, especially and actually before that even a domain expert. Get someone who actually understands what the end user is doing. That's something I think a lot of us in the software space underestimate. So here's an example of traffic flow. So this is simulated using AnyLogic, which ironically is an Eclipse-based software vendor. And what they do is we integrated with them, and we have a reinforcement learning library I'll describe later called Reinforcement Learning for Java that actually integrates with their software and helps run a simulation. So what we're doing here is, again, we're simulating traffic, and we're actually minimizing people at traffic lights over time. So we just sample traffic, right? Like, so you have like 50 people, and you're simulating crowding. What do you do, right? And then reinforcement learning actually optimizes it over time. The baseline right now in the space is actually just standard optimization problems. Instead, we're using reinforcement learning to do it. So we demoed this at the AnyLogic conference in Texas last month. So now that you've kind of seen like some of the, so now that I've explained why does this exist, what space does this exist in, I'll get a little bit into just some of the things we do. So Deeplearning4j itself, essentially it's a whole software distribution. It's not just one library. You have the top level library for kind of model building and deployment. So that's Deeplearning4j itself. So what's going on there? Deeplearning4j itself contains everything from neural nets, right? Like, so, like describing a neural net in Java, like, oh, I want 3 layers and it's a 2-class problem and all. So that's Deeplearning4j. And then we have a Scala wrapper called ScaleNet. Then there's what we call ND arrays for Java. So we have our own kind of like our own NumPy/TensorFlow. So built in there is thousands of mathematical operations. Basically everything you'd find in TensorFlow, or at least most things you'll find in TensorFlow, you'll find in here. We also have a direct TensorFlow runner as well. So one thing that's not mentioned here, but between the 2 libraries, there's something called Java CPP. We write our own Java to C++ transpiler and automatic Java native interface generator. So we don't even maintain our own Java native interface bindings. We generate everything. So we have bindings for everything. We have native bindings for the whole Python ecosystem. CPython itself, OpenCV, you name it. That's also what's binding. That's also what's making ND4j work with all the matrix libraries by Intel and all those other people. We also have libND4j. Like I said, we actually write all of our own CUDA code. So we actually we directly integrate at the C level with like all the libraries from Intel, and we work on IBM Power. We work on iOS. So there's a guy in our community named Johan Voss who works with Java, the JavaFX community, and he's actually built something. He actually helped us integrate with iOS. So he writes Java code on iOS, and we actually run on there. So we do everything mostly at the native level, just like everybody else. We have our own kind of built-in memory allocators and everything. So we do our own memory management transparently in Java. At the native level, we do everything on the GPU, CPU, et cetera. And we do all of our math off heap. If there's any Java people in the room, you'll know that's significant. So we do everything at the native level off heap and on the GPU, all managed for you, and you don't even need to know how it works. We also have our own CUDA distribution. With us, you don't even have to install CUDA. It's all there. So if you've ever tried deep learning and you've had pain setting up the libraries, You don't even have to do that with us. We just exist. And so we're actually a way of packaging every single native library for machine learning, all from Maven Central. So another one is DataVec. So we actually have our own specific ingest library. So you can do, you can do everything from time series. So we have schemas and all that other fun stuff. We also have wrappers for computer vision. So like I said, we have our own OpenCV distribution as well. So we actually wrap all of OpenCV because we generate it. So on top of that, we maintain something called JavaCV, and then on top of that, we have our own library called we have our own computer vision library in DataVec. So we have one abstraction called a record reader. You read in records, and those records could be images, or they could be from a JDBC database. They could be columnar as well. So we actually unify binary, like binary data sources like images, audio, and even video, with columnar in one library. And it just does data loading and transformation. Same diff. So as above, that's our TensorFlow. There's thousands of operations implemented in there. I have a whole team that just does math, that just does low-level, fast math operations. Arbiter. So you want to do automatic generation of models. We do that. So what does that mean? That means that you can set up a configuration and say, give it these range of parameters, and you do automatic model tuning. Reinforcement learning. So as I mentioned RL4j earlier, RL4j did this. So we actually simulated traffic. Model import. So one little known fact is Skymind is also the second largest, even though we contributed DL4j to the Eclipse Foundation, we're also the second largest contributor to Keras. So Keras is mainly done by Google. About 15 engineers work on it full time. And we work very heavily with the Keras community as well. So we advocate that as kind of our Python interface. And then we have JumpI, which is lower level for a lot of our tensor operations. So little known fact about Jumpy is we actually use something called PyGenius that actually integrates via Java. So it goes down to Python reflection, CPython to Java native interface C++, up to Java reflection. And it actually allows us to automatically start a JVM from Python via native, and then directly interrupt with the in-memory Java and C. And Java and C, the Python and C pointers can talk to each other, interop in the same process. So we built Jumpy on top of that. So if you want an easier interface to JVM code, we built it, and we even work with pointers. If you know C code, you can do a lot of fun things with us. So use scenarios, Android apps. So we work first class on Android, so you can work with us on Kotlin or whatever. Closure. So we have a little niche. We have a neat little niche thing in the Closure community as well. The Closure bindings are. I know Jutsu.ai, JUTSU, if Closure is your thing. So we're also the #1 deep learning library on Spark. We're widely used everywhere from Alibaba to GE in terms of the Spark integration. We also, another thing is inference. And so like I said, microservices, really big. So you're not always deploying everything on Spark. So we're the deep learning library that can run on Spark, but doesn't require it. And that allows us to run models from Keras. So that's been a really common use case. So Keras is huge. It's the second largest deep learning framework out there, and we're the #1 way to run it on Spark. And then, as I mentioned Java CPP earlier. We also have our own TensorFlow distribution. So we wrap all the TensorFlow C++. We also bundle the C bindings, among other things. And then we have an easier to use interface on top of that. So depending on whether we have about 3 or 4 different ways you can run neural nets. So depending on what you're doing, like what your use case is, generally, like I said, our niche is kind of the Java virtual machine. We have wide coverage for that. That's what we do. That's what we focus on. So now to elaborate a little bit. So the deployment out there in the community, we've seen Federated Learning. So someone actually built. So Federated Learning is basically where you send encrypted data from the phone when it's plugged in, and what we do is we send small updates to the network So we're not clogging your network, right? So when you send data up, we learn a little bit about you, and then it's all done. It's still done all on a centralized server, but we only learn from you bits at a time over time. We've also been used on ARM, so like I said, we can run on Pis. So if you want to run like a camera and everything else, you can do that. And then we also run on NVIDIA's Jetson. So the significance of us maintaining our own CUDA code and everything else is, again, we can run on everything from small Pis all the way up to the various Jetson machines. So that means ARM plus CUDA. So here's an example of the federated learning part. If you want to see more, this is what I mentioned with the small updates. So I could see federated learning being used in like whole IoT networks as well. So you could be doing more than just sending photos from a mobile app, but maybe you want to send deltas. Maybe you want to send deltas from different factories, and maybe you need to send it encrypted. With that, you can do that. You can do that with us. So for private, for a lot of privacy applications, federated learning is a very interesting new tool out there. So this was the CTO of Azul. So Azul Systems does they do like their JVM vendor, and their CTO actually used us for basically this Raspberry Pi use case, and I think he used it to like do self-driving, like a small self-driving demo, like controlling it from the Pi or something like that. This was a talk that was done at Delvox Belgium a couple years ago. And so from there, it was pretty short. It was just meant to be an overview. I expect there'll be questions. I'll open to the floor.
Hey, sorry if I missed this. Thank you for that. Can you put your information up on who you are?
I suppose. So I'm here. Go ahead and yeah. So chief scientist of Skymind, I created Deeplearning4j.
Cool.
Yeah. So normally based in Japan, I don't normally come back out here. So it's actually rare for me to be in the U.S. So if you have anything, let me know.
I feel like I have a lot of things, but
yeah.
I'll ask you
yeah, offline. Let's go. Yeah, let's do it.
Definitely.
Okay.
Hey, Adam. So when I started the machine learning a couple of years back, all the example, all the tutorials, Google, everybody was flooded with the TensorFlow and Python, right? And very little information was about the Deeplearning4j. Why is that? I mean, when I started looking at the GitHub, and that's why I see the vast, rich examples and use cases. But if you come back from that, if you don't go into that, or if you are not here, I think somewhere this is missing, and that's why I say when I try to enforce this library in my corporate, and there were like a lot of hesitation. No Java, only Python. So is that a typical reason?
So I can't sell to those people. I sell to people who deploy production. So I actually don't. I generally don't try to sell into Python. We import Keras.
Right.
Right. Like so. If you're going to use something, use us in production, and then use Keras for the Python stuff.
Okay, so basically build to the DL4j and deploy in production using the Python.
Right. So okay. So train using Python. Like we're the second largest contributor to Keras as well.
Got it.
So generally, yeah, we use Keras. Import that. You're good to go. Then you can do whatever you want to do.
Okay. Cool. The other question is, how do you train and multi-JVM? So is that the feature? I don't think you mentioned that, but the same model could be like in parallel fashion could be trained. Is that?
Could you clarify? What do you mean? We don't
on the distributed system, right? So the multi-JVM could be training on the same model. Is that something you guys are looking at?
So we just. We barely do anything in Java. Everything's off heap.
Okay.
Yeah, so we just do our own memory allocation, our own memory management. We do our own caching. So basically the reason we're able to own the whole stack is because we only solve one problem. We only focus on math. So one thing we do compete with Java itself. So we actually do semi kind of compete frenemies with Project Panama. They only target Intel chips. We can't use Panama. We have to have our own competitor because they don't work today. We work on GPUs and we can map C++ source code, and we do CUDA. We work on IBM ARM, and we actually work on Android. All we get from them is, oh, it's not real Java and everything else. So we're actually open to more than one Java implementation, and we only focus on the math part, right? Like so we have our corner. That's what we care about. We care more about math on the JVM. That's kind of where the special sauce is. So we also care about running math off heap on thousands of Spark nodes, right? Like so, it's a very specific use case. Lots of companies have, but no one's really done well.
Okay, thank you.
Can you go into a little more detail about exactly what a model is?
Sure.
And how it integrates with the
So a model is just output from source code, such as Python or Java. Generally, it's a large binary file. It's a zip file. It's basically a descriptor of what does this model look like, and what are what it's called its weights. So the weights are just numbers, floats, doubles, that represent the state of the model, right? Like so, basically, when you solve a calculus problem, you have all these variables, right? Like 4 or 5 or whatever, right? And you optimize them, and somehow they get to some optimum, and you just know that they're like 1 to the negative 6 and 0.52, whatever, right? Like so, imagine millions of those saved as binary, floats or doubles, zipped with metadata configuration representing the layout of whatever the neural net architecture is. Now, if you're doing, it is a little different if you're saying doing random forest, right, or whatever. Then that's a different model state. Same idea though. That generally ends up being an XML file. There's a standard called PMML. So for neural nets, it's a little fragmented. Different frameworks implement they might implement like protobuf. We use zip. We use zip plus our own we use zip plus JSON. Everybody kind of has their own format. There's ONNX, Onyx. That's the Open Neural Net Exchange format. So that's another way of representing models. So generally, it's fragmented. They all do the same concept, which is just this is what the model is. This is how it runs a computation, and then this is its state. And again, it's not code. It's saved from code, and generally, it's a standardized format of some kind.
No more questions? All right, so we'll have a break till 3:30. Thank you so much, Adam. It's been really enlightening. Thank you.
Dia de luz, festa de sol, e o barquinho a deslizar no macio azul do mar.